Hello, everybody. My name is Ethan, and I am a CFI in training. It's been a little while since I started my CFI training, and hopefully, weather permitting, next week will be when I take my CFI check ride. But, as is the theme of the channel, let's see if I still got it. In today's video, we're going to be discussing weight and balance. So, for weight and balance, there's a couple of major things that we're going to cover, with one being what is CG, another being how does CG affect flight. CG means center of gravity, and just going to go through and talk about this big term of weight and balance that we've all heard about in aviation. So, in today's video, we're going to discuss these things, define a good bit of terms, and then we're also going to actually do a paper weight and balance form, go through, talk about that, and then also discuss where we find these figures from, these numbers and everything that we use to calculate this, and make sure that we're all good. So, the first thing that we can do is define some terms. So, to start off, CG, that stands for center of gravity. Essentially, center of gravity is just the point on an aircraft at which the entire aircraft's weight or mass is centered. So, another thing to think about with that is imagine that you have a plane, and there's weight back here, there's weight in the engine up front, there's weight on the tip of the wings, in the front of the weight of the people sitting in there or wherever the fuel is. But what we're concerned with center of gravity is that our aircraft, if we were to suspend it from this point of the center of gravity, let's say that I just like set it on my finger right here. If I were to suspend it from this point, it would be perfectly balanced. So it wouldn't tip over this way, wouldn't tip over this way, or this way. It would be perfectly balanced. So that is what our center of gravity is. Our aircraft's weight is centered at that specific point. This center of gravity does change, based on when you, like, let's say that I added new equipment into the plane, or let's say that I brought new passengers in that weigh different, or one sits in the back seat versus sitting in the front seat, or let's say that I burn a lot of fuel in my flight. This CG is constantly changing. But we'll talk about that a little bit further on. Next, we have datum, which a datum is just an imaginary reference line when we're doing the paper weight and balance that I just showed you earlier. And calculating all those numbers, this datum is just this imaginary line in which we get our reference numbers from. So as far as lengths from one point to the next, that is where we get our information from, is this imaginary reference line, or the datum. The next term we have is arm, which arm is just the distance from that imaginary reference line, that datum, to the specific point that we are talking about. So whether that be the seats where the pilot and passengers sit, or whether that be where the fuel is, or whether that be where the baggage is, that would be an arm, would be that distance from the datum to where those things are. And then moment is something that we'll use specifically just with talking about our CG and calculating it. And that's just calculated with doing our weight times our arm. So the weight of whatever the object is, if it's the people or the fuel or whatever it is, multiplied by the arm, or the distance from that imaginary reference line, the datum. And then a couple of helpful terms to know as far as weights go. We have what's called the basic empty weight, which is just a weight that is, we have the weight of the airplane, we have the unusable fuel, so the fuel that can't be pulled out by the tanks, we have the optional equipment, whatever equipment's in there, and then full operating liquids, so like oil and things like that are necessity for the aircraft to run. That's our basic empty weight. So just the weight of those things, no added people, no added fuel, no added anything, just that. Then we have max gross weight, which max gross weight is determined by the manufacturer, and that's just the maximum weight that the aircraft can weigh, the highest allowable weight of it. So we can't go any higher than that. And then lastly, we have useful load, which is just if we do our max gross weight, so the max that we can be subtracted by the empty weight, so the fewest that it can be, is what our useful load is. It's just what the aircraft can carry. So that would be passengers, fuel, baggage, things like that, that are, anything the aircraft can carry. So those are those terms that we're going to be using throughout the video today. So just remember those. And if you need to pause and take notes on these, I would definitely encourage you to do that. So here is just a nice little picture from I believe this is from the PHAC, just on weight and balance. And this shows it on a plane, because I'm going to get a little arbitrary here in a second by describing CG not with a picture of a plane, because I'm not that good of an artist. But in this, you can see right here is this imaginary reference point, the datum. And then there's arms from there all the way to the front and there all the way to the back. And again, that's just the length that they use to determine, if somebody was sitting back here, how far that length is from here to here. And then the CG range, that's what we will call our envelope, our CG range. And we'll talk about that here in a second. But that is what that looks like. So from there on out, this is what I like to use to help with CG. So again, we talked about the CG being the point in which everything in the plane is balanced. If I bounced it on this finger right here, the plane would stay balanced. But again, I can't get it to do that on my finger. But I like to think of a teeter-totter. So on a teeter-totter, if you have two people that weigh the exact same weight and you sit them both on either side, it's not going to go up or down. It's going to stay perfectly balanced, like this one right here. But as I change the weight of some person on it, so let's say that this guy's been eating a little more and hasn't been to the gym in a while, he's gaining some weight, then he will start to come down and this side will start to come up. And that is how, a teeter-totter works. We've all played with one as a kid. So that center point, that fulcrum in the center of that, would be our CG in this example. So again, we want it to be perfectly balanced. We want our plane to be perfectly balanced, just like a teeter-totter when both people weigh the same. So if somebody were to weigh more back here, then we would want to also add weight up here to be able to do that, or redistribute that weight maybe a little bit closer or a little bit further away from this center point, that CG. Because again, this is just a drawing of a lever right here. If I were to push down, and this is that fulcrum of that lever, if I were to push down on a lever at the base of it, the amount of force that I would have to put on it would be pretty great to get it to move. Versus if I were to push down on a lever at the very end of it, I don't have to put as much force for it to go the same distance. So I think kind of about a shovel a little bit. So if I go up and I have a shovel and I'm holding it right by the head of the shovel at the base and I'm trying to scoop, that doesn't work nearly as well as if I get in the back of it, push down on the very end of it, because that makes it a lot easier on me, a lot less tiring. So same thing, in a plane, if we go back to our picture right here, there's never just going to be, like in our teeter-totter example, stuff that's added to this very end and stuff that's added to this very end. It's not how it's going to work. There's going to be some components in here, like an engine is really heavy, or instruments can be heavy, those components. And then people can be heavy, or fuel can be heavy in the wings, things like that. So what's important to note with that is just that with this CG, there's going to be things that are added here. There's going to be things that are added over here and here. And what we're trying to do is just get it to add up to the same amount of force on both sides, so that this CG, this teeter-totter of our plane, will be like this and not tilted either way. So we then talk about a CG range, or an envelope, like we said before. This CG point right here is not the only spot where it'll balance well. It has this envelope, or this CG range, where the CG can shift forward or back a little bit and we still be fine. In the DA-20, which is the plane that I'm going to be using in my example today, the Diamond DA-20, the CG range, or envelope, is about 5 inches in distance. So, it would be from like here to here is how far this CG can move. So if this point wanted to be like right over here, that would be fine. And that would be fine. They would still be balanced. But if it got outside of this, and let's say that my triangle was now right here, it would no longer be balanced. So that is what we mean when we're talking about the envelope. So like we said, just giving you an idea a little bit on how CG works, how we're trying, it's all a balancing act. We're trying to keep ourselves within that tolerance, within that envelope, and keep ourselves balanced because the plane is the most stable. So from there, now we can go through and talk about this form. So right here is that envelope that we were talking about. This is our weight and balance form, and this is from my flight school. Again, we're going to be using a Diamond DA20, so that's where I'm getting all this information from. But this little envelope right here, this whole trapezoid looking thing, I don't really know what it is, a rhombus. This whole thing is what we want our points to be inside of when we chart them, because that means we are A-OK. We're within those two orange lines that we talked about right here. But if we get outside of that, if we get to the point where we are, let's say we plot a point right here, that is outside of that range. Therefore, it's not going to be as stable or as balanced on that point like we talked about before. So when it comes to getting all of these things, we see that basic empty weight, which if we remember, that's just the weight of the aircraft, the unusable fuel, and the liquids that are inside of it that are necessary for it to run. So like oil, things like that. We got this basic empty weight. I had to get this from a specific plane in our fleet because I'm using a reference AFM, aircraft flight manual, for all these calculations. So you can get that from your weight and balance section of your POH or AFM, whichever your plane has. But from here on out, I'll show you where I find this in this reference AFM. So if I get on Canvas and look through here, here's our AFM for the Diamond DA20. If I get in and I look at the table of contents, I'm looking for weight and balance and equipment list, chapter 6. So I will go to page 155, and boom, here's our table of contents for the weight and balance. We're going to want to probably find flight weight and center of gravity. So now we'll go down through. And at this point, we're just getting the numbers that we're going to need that are going to be a necessity for us to do these calculations. So keep going down through. Right here is the table that it looks like for a Diamond DA20 right here. So we can find our arms, that distance from that imaginary datum line to where our spot is at, and now use that for our calculations. So if I look at this, pilot and passenger, lever arm is 5.63 inches. We're going to want to use inches because we're in America, but I guess if you were in Britain or something, you would use meters. But 5.63 inches. So now if I look at my thing right here, I find pilot and co-pilot. That's who we are. Let's say that I am flying by myself right now. So I weigh 170. So I would put my weight in of 170. And that arm we determined was 5.63 inches. And as we determined before, our moment is weight times arm, or the way that I remember it is WHAM, weight times arm equals moment. So if I do, and I have my calculator on my phone, 170 times 5.63, I get 957.1. Cool. So from there, now let's say that I have 10 pounds of baggage with me. I would put that 10 in there, and now I go back to my AFM to see where the baggage lever arm is. It looks like it's 32.44 inches. So now I would get in here, put 32.44. 32.44 times 10, 324.4. So now, to get that zero fuel weight, which is just the weight without any fuel, we're going to add our basic empty weight, our pilot and co-pilot weight, and our baggage. So if I do 170 plus 10 plus 1207.73, I get 1387.73, which I'm just going to round up to 1388, just because it's hard to write with my mouse. And then for moment, I'm going to add up all of those. So 10,000 plus 957.1 plus 324.4. I get 11,281.5. So I'm going to say 11,281, or 282, sorry. So from there now, in order to calculate our CG, we do moment over weight. So the way that people remember that is they say your mom is overweight. That's how you get your center of gravity. So 11,282 divided by 1388. This will give us our center of gravity for this specific point, which it looks like, let me do this calculation one more time. 11,282 divided by 1388. 8.13. Cool. So from there, now that we have, and with this one, typically you'll chart with your CG on an envelope chart like this, but Diamond does it a little weird, so you don't actually use that CG. Or maybe this is just a my school thing, but we have 1388 on the weight, so we'll say 13, 1, 2, 3, 4, that would be 80 up, and then we find our moment of 11,282, so 11, that would be 12, we'd be like right around in here would be our point. Cool. So that point right there is going to be our zero fuel weight, that blue point. Let me make it just a little bigger. Alrighty. Now we would add our fuel. So I just know this off of the top of my head, but our DA20 can hold 24 gallons of fuel. And if I look into this right here, for the fuel, usable fuel load, it's 6.01 pounds per gallon. So I'll do 6.01 times 24. I'll get 144.24. Just for simplicity's sake, I'm going to round down to 144. So 144 for our 24 gallons. And then I want to look in here and find that arm, which it looks like is also 32.44 inches. So now I will put that in there. Cool. So 144 times 32.44 equals 4,671.36, but I'm just going to keep it at 4671. Now from there, we're getting our takeoff weight. So now when we get our takeoff weight, it's important to make sure that it is less than our maximum gross weight, which we talked about is just the manufacturer weight, that if we exceed that, we are outside of the limitations for the plane. So I know in the DA20 the typical max gross weight is 1764. So I'm just gonna say that right there. So if I do 1388 now plus 144, I get 1532. And then 11,282 plus 4671, 15,953. Cool. Now in order to get my CG, I just do that moment divided by the weight. So 15,953 minus 1532, it's going to come to around 10. Yep, 10.41. Cool. So now I'm going to use, let's just say, that color for our takeoff weight. So now I'm finding 1532 on the weight. So 1520 going up right around in here. I'm trying to find 15,953. So 1600 is going to be right around in here. We'll say that's about our takeoff weight. Excuse me. So that is our takeoff weight. Again, we're within that big envelope, this circle or, shape right in here. So we're good. Now, just to determine if we're within our CG the entire time, because again, we're talking about that weight with a CG, and as weight changes, we have to also change the weight and make sure that it's good to be centered on that. But we know that we see our empty fuel is within the envelope, and we see that our takeoff weight is also within the envelope, so we're good here. But we know that however much we burn will also change our weight, because again, each gallon of fuel is 6 pounds, 6.01 pounds, like we just talked about. And then we know that we burn about 6 gallons an hour in our plane. So that's important for us to know. So let's say that I fly for 2 hours, so we'll say 12 gallons. Now I want to do that 12 times 6.01. That gives me 72.12. And from there, we'll just keep it at 72. We remember the arm was 32.44. And I get 2,335.68, so I'm going to say 336. From there now, to get my landing weight, I just do my takeoff weight minus my fuel burn. So however much weight I burnt in fuel. So 1532 minus 72 is 1460 for the landing weight. And then for the moment, we got 15953 minus 2336 equals 13617, which that was terrible. We'll put a little thing. Now 13617 minus 1460, or sorry, divided by 1460 equals 9.33. So now we can chart with this color right here, nice little green color, what our landing weight is on this point. So we've got 1460 right in there, and then 13617. It'll be right around in here. So now we can see that there's a nice little line that we can draw, and this is what our flight's going to look like from the point of takeoff right here all the way to the point of if we had zero fuel. This will always be a straight line on this envelope right here, because there's going to be a constant loss of weight in the fuel burn. But as we can see right here, it is perfectly within that limitation. So, as we talked about before, we have our CG, we have this envelope, we want to keep it inside this envelope. But one thing that we want to prepare ourselves for is, with CG, what if we were outside of that envelope? You know, what if my point was outside of here or outside of here? So a forward CG is left of the envelope in this instance, so I'll use orange. Forward will be on the left, and then an aft CG would be on the right. Forward just means, you know, the weight is more balanced towards the front of the plane, so its tendency is going to be it wants to go nose down. Aft is the weight is more balanced towards the back of the plane, so it's going to want to be tail down, which would be nose up. So it's important now to understand how this forward or aft CG can affect our aircraft's flight characteristics. So with a forward CG, our aircraft is typically considered to be more stable. That is because with a stall, our first thing that we always want to do when we stall is lower the nose back down. So if the tendency of the plane's nose, with the CG being forward and it being balanced to now it wants to lean this way, is let's say that I pull back on this, the plane, if I let go of it, it wants that nose to drop. And that's because the CG is more balanced towards the front. So it will be more stable because it's easier to get um, out of a high nose attitude or just any stall. And then you also will have a reduced range in endurance, so you're gonna have a higher fuel burn. And then because it's going to require more power to maintain the same speed, just because your plane always wants to go down like that. So if I want to maintain an altitude, I'm going to have to add more power to keep that altitude. And then we're also going to have a lower cruising speed and a higher stall speed. An aft CG, or where the tendency of the plane is for the nose to go up, is essentially just going to be opposite that. So you're going to have a faster cruising speed. You're going to have less stability, because if I were to get into a stall, my plane still wants the nose to go up because it's more balanced towards the tail coming down. So it's going to be less stable. We're going to have that lower stall speed, higher cruise speed, and then we're also going to have less drag and a better range. So better fuel burn, meaning we burn less fuel, and we're just going to have a better endurance with those things as well. Let's say that we were to overweight our aircraft. Let's say that I took off and I was way over that maximum gross weight. It would essentially just take us longer to get off the ground, because as we weigh more, we need more lift to be produced in order for us to lift up off of the ground. So when we're taking off, we'll have a longer takeoff roll. We're not going to climb as well. We're going to stall at a higher speed. But essentially, with weight and balance, that's all that we have. Just being able to understand how these calculations work here, understand that we find the information in Chapter 6 of our AFM or POH, typically, the weight and balance chapter. Understanding what these terms are, CG, datum, arm, moment, and then the different weights and useful load. And also just knowing that at most flight schools, you're not going to calculate a paper weight and balance every single time. I'm not going to go out and do these calculations on my own most of the time. Most of the time, I'll just get on a computer, plug it in, it does it for me. But it's important to be able to know how to do this, because again, they talk about in aviation, children of the magenta line. You become so reliant on something else to do the work for you that you become complacent or incompetent at your own job to be able to do it yourself. And as pilots, that's not what we want to encourage. We want to encourage a culture of being able to do the things for ourselves, being able to be competent at every aspect of our job. So just knowing how to do this, and if you have any questions about any of this, you can leave a comment and I can do my best to answer it for you. But that is all for this video, so have a good one.